We found the derivatives of 4 of the hyperbolic functions so far. We only got 2 more to go. Let's look at cosecant inverse of t. Now, the cosecant is 1 over the shine. So remember, the graph of the shine looks like this, exponentially up to the right and exponentially down to the left. So there's the graph of the shine. Now the cosecant would be 1 over the shine. So everywhere the shine is large, the cosecant will be small, and everywhere the shine is small, the cosecant will be large. So if we want to look at its graph, and we can think about the shine, as shine gets really large, then the cosecant gets 1 over large numbers, that gets forced to 0. On the other hand, as shine goes back, as t goes back to 0, the shine is becoming tinier and tinier positive values, and 1 divided by tinier and tinier positives is going to get larger and larger. So we're going to have a vertical asymptote here on the cosecant of t. Similar thing is going to happen over here, but all the values are negative, so we'll get this pattern here in the graphs. So now that means that the graph of the cosecant inverse, well, you just have to switch the x and y axes, but it looks fairly similar. It's a slightly different shape because the pattern of the slopes is different, but it does look fairly similar to the cosecant. So this is the graph of the cosecant inverse. You can't really tell because of my sloppy graph. We're just looking at the general shape of the graph of cosecant inverse. So that works anywhere as long as t isn't 0. We have an inverse for the cosecant. Well, let's go ahead and find the derivative of the cosecant then. So we use our usual trick that y is the cosecant inverse of t. So the cosecant of y is t, and the derivative of the cosecant is the negative cosecant cotangent. So we have the negative cosecant of y times the cotangent of y times the derivative of what's inside, which is dy dt. And on this side we have 1. So dy dt equals negative 1 over the cosecant of y times the cotangent of y. Now we'd like to simplify this. We know the cosecant of y is t, so we can replace this cosecant y with t. We need to find the cotangent, but of course there's our hyperbolic identity that relates the cosecant to the cotangent. So we have, let's see, if we take our usual cosine squared y minus sine squared y equals 1, and we divide both sides by the sine squared, we'll get an identity that has the cotangent and the cosecant. So cosine squared divided by sine squared would be cotangent squared. Sine squared divided by sine squared would be 1. And let's see, 1 over the sine squared is the cosecant squared. So we get cosecant squared y here. Now we want to figure out what's the cotangent of y, and we know what the cosecant of y is, so let's solve this for cotangent. Cotangent squared y is 1 plus the cosecant squared y. So the cotangent of y should be plus or minus the square root of 1 plus the cosecant squared of y, and we know the cosecant is t, so we have plus or minus the square root of 1 plus t squared here for our derivative. So we have this negative 1 up top, and then we have plus or minus. We've got this t from the cosecant of y, and we've got this square root. We've got the plus or minus here and the square root of 1 plus t squared from the cotangent. Now we need to figure out when do I use the plus and when do I use the minus. So that would depend on the sign of the cotangent. When we graphed the cotangent looked like this. It was 1 over the tangent, so it had this. So when will the cotangent of y be positive? Well, the cotangent of y will be positive if the thing that you're taking the cotangent of is positive, and it will be negative if the thing that you're taking the cotangent of is negative. Now, we're taking the cotangent of y, and y is the cosecant inverse of t. So when will y be positive? Well, here's the cosecant inverse of t. If t is positive, then the cosecant will be positive. On the other hand, if t is negative, then the cosecant will be negative. Okay, so in other words, the cotangent is going, if t is positive, then the cosecant inverse of t will be positive. So we'll be taking the cotangent of a positive number, so the cotangent will be positive. On the other hand, if t is negative, then y will be negative, and so the cotangent of y will be negative. So what we should do here is we should use the plus sign when t is positive and use the minus sign when t is negative. And, well, what is it that when you're given a number, you don't change its sign, and when the number is negative, you put a negative in front of it? No, that's the absolute value. So we could just say that, and without the plus or minus, really what's going to happen is we're going to have the absolute value of t. Because when t is positive, we leave its sign alone, and when t is negative, we multiply it by another negative. That makes it positive. So that's essentially the absolute value. So now we know the derivative of the cosecant inverse is the absolute value of t times the square root of 1 plus t squared. And that works as long as t is not equal to 0. Let's do it for the secant inverse as well. We'll find its derivative. Okay, so secant inverse. We should even think about whether or not secant has an inverse, which naturally it wouldn't, because if this is the graph of the cosine, it's growing exponentially to the right and to the left, then the sine, or the secant, sorry, is 1 over the cosine. So 1 over 1 is 1, and then as the values of the cosine get bigger, 1 over the cosine is going to get smaller. So you can see this is the graph of the secant, and it doesn't pass the horizontal line test, right? So it doesn't naturally have an inverse, but you could cut it off. We could cut off maybe the left-hand branch here so that we're only using the right-hand side, and then the secant would have an inverse. And that inverse would look like this. If you flip this, the graph is always between 0 and 1, so the graph of secant is always between 0 and 1, so the graph of secant inverse will have inputs between 0 and 1. We'll start here and then go up like this. So if this is t, then this is the graph of the secant inverse of t. Looks something like that. Okay, so we really only have a secant inverse if t is between 0 and 1, and because of the way we cut it off, we know the secant inverse is always going to be positive. Well, at least greater than or equal to 0. So secant inverse of t is always greater than or equal to 0. Okay, the secant inverse of 1 is 0, because the secant of 0 is 1. All right, well, let's find the derivative by our usual trick. And so we're going to say y is the secant inverse of t, and we want to find dy dt. So we'll take the secant of both sides, or just if y is the secant inverse of t, that means that the secant of y is t. We'll take the derivative of both sides with respect to t. Remember, the derivative of the secant is the negative secant tangent. It's not like the secant, right? Because the secant is positive secant tangent, so it's a little bit different for that one. So we get the derivative of the outside, evaluated the inside, times the derivative of the inside, and that's equal to the derivative of the other side, which is 1. So dy dt is equal to 1, I'll do negative 1, over secant y tangent y. I just float that negative up to the top because it get in my way otherwise. Now, the secant of y we know is t, so we could replace the secant y with t. But we need to work on this tangent of y, and of course we go back to what we always go back to, is that the cosine squared of y minus the sine squared of y has to be 1. And if we divide both sides by cosine squared, we get 1 minus the tangent squared of y is the secant squared. Okay, and we want to find the tangent, so I'm going to move the tangent squared over here and the secant squared over there. I'll get tangent squared y alone on one side, and then on the other side, I'm going to bring the secant squared over. I'm going to have 1 minus the secant squared. Okay, so the tangent of y is the square root, is plus or minus the square root of 1 minus the secant squared of y. Okay, so, but we know that y, secant y is t, so this is the square root of 1 minus t squared. So we have for the derivative then negative 1 over plus or minus from this tangent t times the square root of 1 minus t squared. We just need to sort out this plus or minus business. Okay, well, the secant inverse only works if t is between 0 and 1. And if t is between 0 and 1, then we know that, let's see, so if t is between 0 and 1, then we're taking the secant inverse, oh yeah, a number between 0 and 1, we know that y is positive, right? And if y is positive, we know the tangent is positive, so didn't really need to worry about the plus or minus. We've now got the derivative of the secant inverse. It's negative 1 over t times the square root of 1 minus t squared. Of course, that only works, though, for t between 0 and 1, because, well, actually got to leave out 1 because even though secant inverse is defined at 1, the slope there is infinite, and so the derivative is not defined at 1. So to summarize, we have these basic derivative rules. If you write them in sort of their chain rule form, so you think about the arcshine not of x but of some function of x, you get 1 over the square root of 1 plus u squared du dx, right? If the actual variable here had been x, if that function had been x, then that would just be 1, and you get the rules that we were getting. So these are the derivative rules that we've come up with, along with their restrictions here, and that's what they look like. Now, the most useful way these come up is when you're actually going the other way, and you recognize this function and you want to find its antiderivative, and it's arc-trig function. So with a little bit of work with these formulas and substitution, you can get these integral formulas. So remember, if you're integrating a squared, 1 over 1 minus x squared, that was the hyperbolic tangent inverse and the hyperbolic cotangent inverse had that same derivative. They just applied in different places. So we can use those. They're sort of complementary to find the antiderivative of this. We get a piecewise function. If the value of u is small, close to 0, then we're using hyperbolic tangent. If the value of u is big, then we're going to use the hyperbolic cotangent inverse. So we have these rules there. So the point's probably not so much to memorize the derivatives of hyperbolics, although it was a good chance for us to practice our implicit differentiation. The idea is, if you see these formulas, they look an awful lot like the formulas that we learn for arc-trigs. So if you're trying to do an integral and it involves a formula like this, then you can think, oh, if it's not quite an arc-trig, perhaps it's an inverse hyperbolic, and then go look those up.